Alright, for this video what I want to do is I want to do some work on drawing Bode plots, Okay, I'm going to do a problem 6.3b, but before I do that problem, I want to just talk about Bode plots in general, okay? You've got two things for a Bode plot. You've got magnitude and phase. Let's look at magnitude first. The problem 6.3b is a third order system, but because the systems that we're dealing with are linear, because it's a third order system, it's factored into three first order systems, and three first order systems multiplied together in the gain and phase domain are basically just everything added together. That's just kind of how it works. You add the phase together, you add the gain together. Okay? So let's look at a first order system, and let's look at the form G equals some gain over tau s plus 1. And let's see if we can create a gain and phase plot from this, okay? So let's do gain first, okay? And so in order to do gain, what we have to do is we have to do, I'm going to say the magnitude is the norm of G, which is equal to the square root of G star G, where G star is the, is the complex conjugate of the of G, okay? So what you do is remember Bode plots are all in the complex domain, so we're going to plot magnitude on the y-axis and then we're going to plot frequency on the x-axis. So what we need to do is we need to substitute S equal omega j, right? So omega is the complex variable, radians per second, and j is the imaginary component. Remember, this all relates to the fact that, when you have a differential equation, what is this? This is tau s, so it's tau x dot plus x equals kf, right? This is our first order system. Our homogeneous solution is equal to a e to the st. S is our complex variable there. And when you solve this, if s is in this case it's first order, so that's not true, but if you get s equal to omega j, what you get is that x of t is a e to the omega j t, which factors out into a1 cosine omega t plus a2 sine omega t. Everything relates to the frequency domain when we're doing Laplace transfer functions. So what we're looking at is the fact that the system is going to, if I apply a sinusoidal input, how is the output going to get affected, okay? And so that's essentially what we're looking at here. So when we're doing Laplace transforms, what we're looking at is going from the time domain to the frequency domain, and it's because of this sort of Euler's formula that says that e to the I theta has cosines and sines in it. So it's going into the frequency component, frequency domain, where things are rotating, versus the time domain where things are linear. Okay, so if I substitute in, let me get my cords out of here. If I substitute in s equals omega j, I'm going to get that G star is k over negative omega j tau plus 1, and then G is k over omega j tau plus 1. If I do G star G, I'm going to get a k squared all over, and I have to look at this here. I'm going to get a omega j times omega j, which is going to give me a j squared, which is negative 1. The negative 1 is going to cancel with the negative, so I'm going to get omega squared tau squared. So I'm going to get omega squared tau squared plus 1 and 1 is 1, and then the complex conjugate goes away. And then I do a square root. So the square root m, my magnitude, is the, I'm going to get k times 1 minus the square root of omega squared tau squared plus 1. Okay? So if I look at this, I can do a couple things. First, I can compute what's called the DC gain. DC gain. The DC gain is when omega is equal to 0. Okay? The magnitude when omega is equal to 0 is pretty simple. It's k. Okay? And you could have gotten that from the gain over there, but it doesn't matter. You get k. So the DC gain is k. if you were plotting simply magnitude, right, m, and you weren't looking for, what's the word I'm looking for here? You were not looking for decibels. Typically Bode plots are plotted in decibels, but if I was just plotting the raw magnitude, when omega was 0, right, this is omega on this axis, this would be k. That would be my DC gain. The question is how does this graph look as I propagate forward, okay? There is a special value for magnitude plots, and if you take the magnitude over the DC gain, and I get 1 over the square root of 2, which is equal to square root of 2 over 2, which is equal to 0.707. This is a special number because if I do decibels, which is 20 log 10 of n, let me get my calculator out. How do I do this? Calculator. I need to turn on the fancy calculator. If I do log of 0.707 times 20, I get -3. This minus 3 dB has a very special name. It's called the cutoff frequency. And it's basically, I'm going to call this k over root 2. I want to know where the graph crosses that point, and it's pretty simple. It's when omega equals tau. So that means that tau is my cutoff frequency, which is why we write things in this form, right? Because it basically, we know that my output is going to be 70% of my input at my cutoff frequency. And so at tau, I am here, okay? After that, you have to use some special rules. For a first order system, the gain drops off at 20 dB per decade. And a decade is a power of 10, and then 20 dB is so on and so forth. And so your first order system is going to look like this, where this here is it's a negative, minus 20 dB per decade. You get your DC gain. And I'm kind of being weird here. I'm going to go ahead and say that I'm plotting this in dB. So my DC gain in this case is 20 log 10 of k. I don't know what that is. K is a variable. That's just what it is. This is not minus 3 dB. This is going to be 20 log 10 k over root 2. Okay? Now, if I divided everything by k, well, then everything would shift down to 0 dB at the DC gain, and then this would be the minus 3 point. But anyway, so there is your gain plot for a first order system. So if you have two first order systems put together, what you can do is you can just add the DC gains, draw the cutoff frequencies, and then draw the magnitude from there. Okay? So now let's look at the phase plot for a first order system. Okay? So let's see here. Let's do, let's post this on the Rocket Books. Scan. All right, so now let's look at the phase. I think what I'm going to do is I'm going to keep G here, so I'm going to erase this. All right, and in order to get the phase of G, you have to take the, and I'm gonna mess this up here. I think it's the phase of the numerator minus the phase of the denominator. Yes, it is the phase of the numerator minus the phase of the denominator, okay? So you have to take the phase of the numerator minus the phase of the denominator. And so let's look at k. So we have to draw this in the complex domain. So this is real and imaginary. Here's k. If I draw a vector from 0 to k, and k is a number and it's constant, the phase of k is always going to be 0. Cool? Let's look at omega j tau plus 1. Let's draw another diagram. Real and imaginary. If I draw 1 and let's see, omega j tau, and I draw a vector, when omega is 0, my phase is 0, but when omega is infinity, my phase is 90 degrees, right? When omega goes to infinity, so this vector is just going to get bigger and bigger and bigger and bigger and approach infinity, okay? So that means this is pretty simple, right? The gain of g is 0 minus, I don't know how you want to do this. It's when omega is equal to tau, so when omega is equal to tau, you're going to get, sorry, 1 divided by tau, I'm sorry. Did I do that? Oh crap. I did that gain plot wrong, right? The cutoff frequency is 1 divided by tau, right? Because that would have given you 1 over tau squared times tau squared. Dang it. Okay, the cutoff frequency, I'm sorry, good thing this is in the same video. The cutoff frequency is 1 over tau, right? Let's redraw this. If you do m, you're going to get k over the square root of omega squared tau squared plus 1. And so omega needs to be 1 over tau, because then you get 1 plus 1 is k over root 2. So the cutoff frequency is 1 over tau. I'm terribly sorry. Okay? So when omega is equal to 1 divided by tau, you're going to get, your complex number is going to be 1j plus 1. So this is going to be 1 and this is going to be 1, which means your phase is 45 degrees. So that means you can kind of connect the dots here. This is my frequency and this is my phase. I should have drawn this the other way. That's fine. Yeah, I'll draw this the other way. I'm going to draw this up here. So when omega is 0, it's 0 minus 0, so my phase is 0. When omega is equal to the cutoff frequency, which is 1 over tau, it's negative 45. And then when omega is infinity, it gets minus 90. So basically I have a data point here and I have an asymptote at minus 90. And so I basically have this whoop, like that. Cool? Okay, so there is gain and phase for a first order system. So I think I'm gonna pause this video here, and just so if you want to just watch this, you can kind of watch this and say like, oh great, that's how Bode plots work. And then in the next video, I'll show you how to do first order or a third order system where it's 3 first order systems multiplied against each other. Okay, and then I'll also post a companion video on how to do this in Python. Great. Happy good night. Great.